I'm Holger Haas. I'm a staff research scientist here at IBM Quantum. Today, I'd like to give you a little bit of a walkthrough of what has been our trajectory here for building quantum computing hardware. And with an eye to the future, I want to lay out for you what we're currently working on and why we're so excited about it. The outline of my presentation is as follows. First, I'll start off with a brief intro to quantum information carriers, or qubits, and specifically the kind of qubits that we use here at IBM Quantum. I'll give you a two-slide introduction to circuit quantum electrodynamics to bring us all to the same page. And then I'll flash you a photograph of what our quantum systems looked like 10 years ago. This will set the scene for understanding how far we've come in progressing with a variety of engineering challenges that building an error-correcting quantum computer requires us to do. And we'll look at various examples of these engineering challenges that we've tackled, specifically control electronics, wiring, packaging, gate errors and chip performance outside of gate errors. Then I'll turn my focus to the future and touch very briefly on the error-correcting codes that we intend to implement with our future hardware and lay out our plan for it. As you might already know, the distinction between classical and quantum computation lies in the fact that for encoding and processing classical information, you need an information carrier with a binary state. For example, voltage that you threshold to arrive at a binary variable with 0 and 1 state will suffice. And that is essentially what is used in classical computers. For quantum computation, however, you need an information carrier that can encode any state in the Hilbert space. In this slide, this any state is represented by these two complex numbers, alpha and beta. But of course, you need a little bit more than that for the quantum computer to be useful. What you need is you need to be able to encode multi-qubit states and perform arbitrary operations on it, usually in the form of a universal gate set. And you also need that information to survive sufficiently long that you can perform these operations. Usually we say that the quantum state needs to remain coherent. Finally, we need quantum information to be accessible. We need a means for reading out the qubit state, and that has to be efficient. So all this starts to sound like a bit of a shopping list. In the literature, these are what are called DiVincenzo criteria. At IBM Quantum, we build quantum computers using superconducting electrical circuits. And specifically, the circuit element that we use as a qubit is called a fixed frequency transmon qubit. However, before I tell you about that specific qubit, I want to first motivate why would we even turn to superconducting circuits. As I mentioned in the last slide, a key requirement for building a quantum computer is the survival of the quantum information, which essentially translates into wanting as little loss or dissipation in your hardware as possible. From that perspective, superconductors have that really desirable property. They come with no resistance or no dissipation. Now, of course, that doesn't actually mean that you have no loss. In fact, there are other types of loss, but it is a great start. Secondly, the second nice property of superconducting circuits is that they're electrical circuits. So that means that you can engineer them, you can design them just like any other electrical circuits. You can use the same tooling, both for design and manufacturing. This is highly desirable, and you can extend these circuits. You can add these extra qubits to your hardware, and you have the scalability component satisfied. Third, and very importantly, quite like with implementing classical logic, you need a nonlinear element. In the case of classical logic, this comes in the form of transistors. Here, superconducting circuits provide you a native element called the Josephson junction, which circuits make use of everywhere. This lies at the heart of our qubits. Finally, we have to acknowledge there is a price to pay. None of this comes for free, and for being able to build and control these superconducting circuits, we have to operate at millikelvin temperatures. However, most quantum computing platforms do need some kind of cooling anyway. At IBM Quantum, we build and operate qubits called the transmon qubit. The transmon was first proposed in the reference that we give here in the slide nearly 20 years ago. What it consists of is two elements. A Josephson junction, which in the circuit that you see there on the right-hand side is given by that box that has the cross inside, and a capacitor. If you actually look at one of our devices here on the left, you see that we engineer a capacitor by fabricating two paddles. The size of these paddles is order 100 micrometers in length. You see one there in that magnifying glass. In between these paddles, we fabricate the Josephson junction structure, which is much, much smaller in size. It's only about 100 times hundreds of nanometers big. And I give here the image of that in the middle of this slide. You see these tapered leads that come together. Both of these leads lead to either one of the capacitor plates, and where they come together, there's a very, very thin non-conducting barrier about 1 nanometer thick that's in between them, and that forms the Josephson junction. Now, what you can do is you can work yourself through these equations that are on this page, and you can show that effectively this object behaves as a nonlinear inductor. Now, why do we go through all this bother? The reason is that when you build such structure, then what ends up happening is that it behaves as a nonlinear oscillator. And the nonlinearity manifests itself in the fact that the energy levels of that oscillator have uneven spacings. So the energy level between 0 and 1 is different from the energy level from 1 to 2, and so on and so forth. So when we want to address it with microwaves, for example, we can isolate the 0 to 1 transition, and we won't hit the 1 to 2 transition as we drive the 0 to 1 transition. And that's critical for being able to build a quantum computer. Finally, it turns out that transmon has also some nice noise resilience properties that were deduced in that paper, also cited here. It is exponentially insensitive to electrical charge noise fluctuations in the environment, which leads to long coherence times. That's why we love it. Coherence time, as I said, is jargon for the survival time of the quantum state. Now, if we want to calculate the frequency of the transmon, then what we need to do is consider the elements that go into that transmon. Now, you see from the circuit diagram, there's only two elements really in it. There's the capacitor and the nonlinear inductor. So as you might guess, what you need is to know the capacitance, and for the inductor, you need to know the critical current of the Josephson junction. And from that, you can back out the energy or equivalently the frequency of the transmon. So there are other things that we can build with superconducting elements. For example, we can build resonators. On the right here, you can see a resonant circuit that consists of a linear inductor now and a capacitor instead of a nonlinear inductor. Equivalently, you could also consider a single mode in a transmission line that would also give you a resonant structure. For example, in this magnifying glass, you see a coplanar waveguide, and a single mode of that, maybe the lowest harmonic, would give you a resonant structure like that LC oscillator here. Now, the distinction between that and the transmon qubit is that here all the energy levels have an equal spacing. When you drive one of them, you drive all levels with the same frequency omega. What you can do with resonators is, for example, you can couple them to your transmon qubit. You can put a capacitor between this resonator and the transmon, and putting a capacitor between the transmon and the resonator could be as easy as just leaving a gap between them. And what you'll find is that if you get this right, and in certain regime, for example, in the regime of far detuned resonance mode, where the resonator could be at 7 gigahertz and your transmon at 5 gigahertz, then the frequency of the resonator becomes very weakly dependent on the transmon state. And what that is useful for is you can use this to detect the qubit state of the transmon. And this is exactly how we do it. Moreover, what the resonator is also useful for is for preventing the transmon from decaying, because if you make it off resonant, then at 7 gigahertz, it cannot accept the 5 gigahertz photon from the transmon. The math just doesn't work out. So now you have protected, we call it Purcell protection, the transmon from emitting a photon into the cavity. Finally, we can use this resonator for driving single qubit gates of the transmon. Here, we would need to use higher powers because we would drive them resonantly with the transmon, so at 5 gigahertz instead of 7 gigahertz for the resonator. But that's in some sense good, because that means that the distortions that the waveform experiences moving through that resonance structure at higher frequency are kept minimal. Now, one last thing to note about this magnifying glass image here on the left is that the resonator here on the left is actually not a readout resonator at all. That is a coupling resonator, but it's kind of hard to tell that because from the looks of it, they look pretty similar, but you have to trace them. And here you see that this one is connecting one qubit to another. That means it's a coupling resonator, but a resonator that connects a qubit to one of these triangular shapes on the edge of the chip would be a readout resonator, because that would connect the qubit to the outside world. Now, moving onwards, we start looking at the first experiment that one could really consider. And already here, with just applying 2 gates and a measurement, we start seeing some little bit of complexity that happens when we run an experiment on a quantum computer. What we do here in this circuit diagram, we apply a Hadamard gate and a Y gate on a qubit, and after that we apply a measurement. What actually happens when you press Shift Enter in your Jupyter notebook to run this circuit is, after you waited in a queue for this to be executed, then this circuit gets loaded onto the control hardware, and the control hardware will emit microwave pulses that get sent to the chip that's in the dilution fridge. And these control pulses, first for the gates, for that Hadamard and Y gate, travel down the cabling all the way to the chip from room temperature to millikelvin temperature stage and excite the qubit. And after applying the gates, we send in a pulse at a different frequency, resonant with the readout cavity, which is at frequency omega, and record back the signal that comes from the fridge to measure the qubit state. So having given you a little bit of a flavor of what happens when we do an experiment, I now want to show you how we used to run these things roughly about 10 years ago. So here what you see is a setup that we would have had in the lab 10 years ago. On the left, there is a full rack, roughly the size of a household fridge or so, full of microwave electronics. And this would have controlled order 10 qubits or so. In the middle, what you see is a dilution fridge. And the dilution fridge has these various circular plates. These are stages. And when we operate the fridge, then the fridge is closed. You can't see inside there. And it's all evacuated. So then these various circular stages are thermally isolated from one another. And that means we can keep them at different temperatures. And the way the fridge is built is that the warmest stages are at the top, and the coldest stage is the one that's the most bottom stage here. And that one is at about 20 millik above the absolute zero, or 0.02 Kelvin. That is where we mount our quantum chip. But to even mount our quantum chip there, we need a way of getting the signals that I just talked to you about, the control signals and the measurement signals, in and out of the chip. So we need some way of routing the signals onto the chip, and that means we need connectors, we need cables. So you can see that inside this fridge there are these coaxial cables that run vertically that carry all of these signals, and the chip itself is mounted onto this printed circuit board, or PCB, the bottom side of which has about 10 connectors that the coaxial cables would have mounted onto. And only on the right, there's this about a quarter-sized chip that has about 10 qubits on it. So all this infrastructure is necessary to control about 10 qubits. Now, if you stare at this image for a little while, you start realizing that having qubits and having that chip there on the right is not all that you need. You need more than that to build a quantum computer. You need packaging, you need cabling, you need room temperature electronics, all of which to support scaling this effort up to numbers that can support error correction or even utility scale workloads. And these pose engineering challenges, exactly the kinds of which we've been tackling for the past 10 years and we continue to tackle. So now I will tell you what has changed, what has been the progress that we've made over the past 10 years. So first, I'll walk you through how has our control electronics evolved over these 10 years. So bottom left is an electronics rack with commercial off-the-shelf electronics, and it's a full rack, like I said, about the size of a household fridge, and this could control and read out about 5 qubits or so. As you can imagine, if you want to do hundreds, thousands of qubits, this would fill up an enormous amount of space, and it would also cost a lot of money. Now, what we've been doing, we've been developing hardware for minimizing the footprint as well as cost the control electronics. And we've been going generation after generation from 20 qubits to 40 qubits to 400 qubits in a single rack in our most latest iteration of room temperature electronics. We can now, in the same footprint, control and read out 80 times more qubits than this commercial off-the-shelf electronics could do, and for a lot smaller price tag. So we're extremely excited about that. And of course, we keep on working on pushing that even further. Second, like I said, what we need to do is we need to get these signals in and out of the chip. How we do that? Back in the day, in that fridge, you would see coaxial cables. These were the vertical metallic lines that were running inside the fridge. Here we have a close-up image on the left of that. It's a further iteration of that. It's our past high-density coaxial wiring example. But in our present setups, what we turn to is cryogenic flexible wiring. What that is, it's this cardboard-like sheet that packs a lot more signals, 70% higher density of signals than the coaxial wiring, and it helps us actually reduce the number of connectors and components that we need to connect to wire up the devices. So that limits the number of things that can also go wrong. It's a great way to take out engineering risk from the setup. Furthermore, it reduces cost in our systems, and over the next year or so, we aim to increase the density of wiring by another factor of 3 or so. Moving on, 10 years ago, what we had in that photograph was a chip that we basically put into a PCB, and then the way we connected it to the PCB was we wire bonded from the PCB onto the chip. Now, that works fine as long as the topology of your quantum computer is either a line or a ring. But unfortunately, this is not how we want to build a quantum computer. So we had to move on from that. Moving away from the single layer of metal wire bonded to the PCB in the previous slide, that was our first generation of packaging technology. We then turned to flip chip technology that you can see in this. Different chips that have two distinct roles. We have a qubit chip and an interposer chip. The interposer chip has a role of routing signals to the qubit locations, and we also use it for placing readout resonators near the qubit chip. The two chips are bonded together using superconducting bump bonds, which are there in the image wedged between the two chips. And the interposer chip is connected to the outside world, which is the PCB, using wire bonds, which are these wires that come in from the sides. This technology was used, for example, in our Hummingbird processor. Now, this helps us a little bit because it gets us to nearest neighbor coupling architecture. It doesn't constrain us to only linear or ring topologies, so that's great. But it has some drawbacks. For example, when we route the signals on the interposer chip, then the metal layers there are not shielded, which means that when we go past the qubit, we can inadvertently have crosstalk to qubits that we don't want to have crosstalk to. Moreover, we have only finite real estate there on the periphery, and we would like to increase the amount of signals that we can get in and out of that interposed, for which we have to turn to our generation 3 packaging technology. So here what you see is multi-level wiring technology. What we've done is we've still kept two different chips, still the qubit chip, where we fabricate our qubits. We still have the interposer, but at the bottom of the interposer, we have multiple layers of metal and dielectric that are insulating metal layers from one another and effectively